Hey, Yuan.
Hi, Charlie.
Yes. Shall we start? We mean one more minute. Yeah.
Yeah, let's wait for like 1 to 2 more minutes. Wait for everyone to join.
Hey, Yuan.
Hi, Charlie.
Yes. Shall we start? We mean one more minute. Yeah.
Yeah, let's wait for like 1 to 2 more minutes. Wait for everyone to join.
Hey, Yuan.
Hey, everyone. Welcome to the XCamp USACO solution discussion for the first competition, December competition for Bronze Division. And let's wait for 1 more minute to get started. Thank you. Okay, so let's get started. So my name is Yuan, and I'm a co-founder of XCamp, and we have another co-founder, Charlie, here. And today we'll be hosting the XCamp USACO solution discussion for the December competition, Bronze Division. And today's agenda will be, we'll first do a quick introduction of XCamp and our teaching philosophy. And then we'll have our first student who entered. Today we'll be hosting. Who entered the USACO Platinum Division several years ago, and he is also my student. And his name is Alex Zhu. And after that, we'll also briefly introduce the XCamp classes and also give you some tips about how to prepare for the next USACO competition and what's XCamp's offering to support you here. Yeah, next slide, please. So to a quick introduction, XCamp is a Silicon Valley-based coding academy, and we provide the serious coding education from beginner level all the way to master level. Like students go to US camp, national camp. And we have 4 students go to the camp this year. And for the curriculum, it was developed by seasoned coaches, IOI medalists, USACO veterans. They are platinum level or higher, and also NOI, IOI medalists. And also we have senior engineer leaders, and they are come from the Silicon Valley, and they are part of the teaching team as well. So our teaching system is very solid and is proven. As I said, we have 4 campers this year, and we already have heard some good news for this year as well. And we have a good USACO passing results in all the lower level as well. So we hope with the XCamp's help, you can get past the USACO levels easier, and we hope we can change the world together with coding. And we think wherever you are and whenever you are, we hope to help you to get better in coding in general, and also get a solid foundation. Next slide, please. So our coding education is mainly about, in beginner level, we want you to love coding. In the intermediate level, complete knowledge. And going forward, if you want to go with the competition, that's fine. And we will support you with the best resource and best coaches. And if you just want to stop somewhere and then enjoy coding, that's fine too. We think it's really good for you to have good foundation so that you can have a very, very good starting point in academia or industry when you enter college as well. It's gonna kind of serve as a lower bound of your life. And we are confident that you'll be able to very easy to get into some top of the technology companies once you finish the complete curriculum or at XCamp. Yes. So next slide, please. That's pretty much it for the brief introduction, and we'll hand over to Alex Du. He passed the USACO Gold and entered USACO Platinum level, I think it's 2 years ago, and he is one of our best students at XCamp, and he started from beginner level at XCamp. So we'll hand over to him. Thank you.
Thank you, Teacher Ren. I will now screen share a whiteboard and begin the analysis on the bronze problems. So let's start with problem 1 of bronze. Let's first go over a quick recap of what the problem is asking. So the main points is that there are n cows. Each cow is willing to pay CI amount of money to get into to attend Farmer John's University. And if Farmer John charges a tuition greater than CI, then that cow will not attend. Otherwise, they will attend and pay the tuition money that Farmer John has requested. So we must choose tuition money. Let's just call it A. Right? Okay, so now first, let's do a quick intuition, what we should think when we first see this problem. First observation we make should be that the amount of money that Farmer John ends up choosing should be equal to some value of CI, right? Because otherwise, if the value of the tuition money is not exactly like a CI, it's in between I don't know, let's say CI and CJ, and it's not actually one of these values, we can see that if we just increase the tuition money to CJ, the same number of cows will attend a university, but then Farmer John will just get more money because she's charging more for each cow. So first intuition, first observation, A should be equal to some CI. Now with that out of the way, we can see that if we sort the array of the next observation we can make is that let's just try choosing A to be any value of CI. Let's loop through all values of CI. Try A being any value, all values of CI. That's the most intuitive solution, right? After we make the first observation, let's just try all of these, all these solutions, all these numbers, and let's see if it works. The issue here is that there are n is less than or equal to 10 to the 5th. 10 to the 5th. So if we choose all values of C, there could be possibly 10 to the 5th distinct values of CI, right? 10 to the 5th distinct values of CI. And if we just directly compute, if we do the brute force solution of choosing A to be every value of CI, then calculating the cost, if the cow is willing to attend and how much the cow would pay, then the amount of the time complexity here would be n for the number of values of CI, for choices of CI, and then n for calculating the total amount of money that Farmer John makes. And we can quickly see that this is n times n squared, which does not work for n less than or equal to 10 to the 5th. Okay, so now, but however, this solution will work for the first 8 test cases, and this should be a good starting point for solving this problem. So now let's go on to the complete solution of the problem, after we have this and n squared solution. Let me just erase this. So what we notice is that we can actually most of the cows, if they attend, they'll be paying the same amount. They'll be paying the tuition money, which means that from this observation, we can see that instead of like counting for every single cow how much they pay, we know how much they'll pay. We just need to see if the cow is paying or not. And if a cow, to see if the cow pays or not, we just have to see that if CI is less than or equal to A, then the cow pays. So we just need to count the number of cows instead of like counting the number of money, the amount of money. And to do this, we can see that an efficient way to do this for all values of CI is, let's try sorting the values of CI first. Sorting CI. And then if we sort CI, we can see that as we loop through the values of CI, so let's say for the sample equation is 1, 4, 6, 4, 6. If we sort this, we'll get 1, 4, 6, 6. We'll see that if we pick a value of CI, let's say we pick 4, then the number of cows that can attend is all cows to the left of this number, right? Because it is a sorted array. And this allows us to get the value of the number of cows we want extremely easily. Because it'll just be the index of the array. So as we loop through it, for 4, it will just be 1 and 4. And if we take this next number of 6, we'll be able to pick all these 3. And if we take this 6, we'll be picking all of these. So we can see that the actual solution, it should be the other way around. We actually want to sort from, well, if we have 1, 4, 6, 6. After we sort it, it's the other way around. If we take 4, it will be able to pick all the cows from to the right of it, as those cows are willing to pay more. And as we like shift left, there's like less and less cows are able to take. So through this, we are able to count the number of cows that are willing to pay this tuition money. And the final answer just becomes I, which is the index. It just becomes I times CI. Well, M minus I times CI. As we loop through this array. Is the solution clear to everyone? Okay, so with that, let's start the next problem then. So problem 2. Let me quickly go over the main points of the problem. So Farmer John has n cows, n less than or equal to 10 to the 5th again. Each one is one of 2 breeds. 2 breeds, either H or G. G or H. Next, these cows occupy these pastures from 1 to n, so it's just like the number they're on. And then next is Farmer John plants grass, like 2 types, one type of cow likes one type of grass. We can just call it H or G again for G or H again, because it's like the type of cow that likes it. And then each cow must be within K of the type of grass it wants. It likes. So, and we want to minimize the number of total types of patches of grass we have. The initial intuition here, the initial observation we should make is that in order to minimize the amount of patches of grass, we want each patch of grass to cover as many cows as possible, right? So each patch of grass should cover as many cows of the type as possible. Now, this intuitively makes sense just because we want to be minimizing the number of patches of grass. So if one patch is able to cover 2 cows, instead of doing 2 patches of grass covering those 2 cows, well, if 2 cows are here and here, if one patch, we want to put one patch in the middle to cover them both instead of 2 separate patches covering them individually. So that's the intuition we want here. Now let's see how we can potentially minimize this. So the solution is just, there's like no real intermediate solution. It's just a greedy algorithm. We want to only put patches of grass when we need to. And when we put patches of grass, we want to make it so that it covers the most it possibly can. So greedy solution, only put patch when needed. And make each patch cover as much as possible. Cover as much as possible. Now, let's see how we can possibly do this. So let's say we have, let's just use the sample test case of, let's say 5, 1, G, H, H, G, H, GG, I mean, G, H, H, GG. We can see that on the first cow needs to be covered by something. And so that means that the first cow must have a patch of grass. But in order to make it, so that covers like if we just cover each cow as we loop from left to right, that means that it will satisfy our first condition of only putting patch when needed. So if we see a cow that's not covered by like a previous patch, then we just make it have a patch. So it's to cover the first condition, all we need to do is loop left to right. Right. If cow uncovered is uncovered, we must need a patch. We must add a patch. Now it's on to how to satisfy the second condition, making each patch cover as much as possible. So we can see that like through our greedy solution, as we're looping left to right, we can see that all cows to the left of each, like the current cow, must already be covered, because from our condition, as if a cow is uncovered, then we already added a patch to cover it. So that means that we just want the patch to cover as many cows to the right of the current cow as possible while covering the current one. So because we don't care about any of the cows to the left. So that means that if we're trying to cover if we're trying to cover this cow, we want this cow to be on the leftmost edge of the patch. So then that means that we want the patch to be K ahead of this. So in this situation, K is 1. So we want the patch to be this plus 1. So the patch will be placed at this location. Obviously P for patch. And then it will end up covering this on the leftmost edge while also extending right one more. So this is the optimal location to place the patch for this example problem. And then going back onto the sample, if we like see the next cow, it will be H. We see that this is uncovered, so we want to again put the patch one more to the right of it, and then the catch will be here. Just label the patches. So this would be a G patch, and this would be an H patch. And this H patch would actually cover both these cows, like to the right of it as well. And we just continue looping down the array doing this. So the actual like code would be if cow uncovered at I, patch of that kind at I plus K. Because this means that this patch will cover this cow on the very leftmost edge of it, while also extending as far right as possible, which satisfies the second condition. The only like possible thing that can go wrong with this is if I plus K is greater than N. So if I plus K greater than N, then we must do like a separate thing. But again, this isn't too hard to like cover actually, because all we need to do is we can just place it like we can just place the patch at location N instead, and it will still cover everything like the cow it needs to cover. And if location N is already covered, then we can like there's two types of patches. And if one of the patches is already occupying location N, then all we can do is just place the second patch at location N minus 1. And in this way, it is guaranteed that all the cows will be covered. Another question you might be asking is like, how do we guarantee that using this algorithm, we're not ever going to place two patches of like different types on the same location? Now, the answer to this is because we're placing at location I plus K every time. Since I is different for every single cow, we're only accessing each I one time. I plus K is also going to be different every time, unless it's this one edge case. And this means that I plus k, since I plus k is different, all the patches we're placing are going to be on different locations, so they will never overlap. And this is, in fact, like a working solution. Does anyone have any questions for this problem? Okay, I'll assume that's a no and move on to problem 3.
Yeah, Alex, there's a one hand raised up.
Lily,
Lily Yue.
Lily Yue, do you have a question or?
Lily, are you there? No. It's good. Let's
Okay,
continue.
I guess not. All right, let's go into the problem 3. So problem 3 is by far the hardest problem of this contest. I'll just quickly go over again some key details about this. So the main details is we basically must design, we must see like if it's possible to design a set of conditions. Actually, let me just go back to the input. Rephrase this. Basically, there's going to be, we think about it as like n rows of binary numbers. Each one, actually no, m rows of binary numbers. Each row has n binary number, like binary and zeros or ones inside. 0 or 1s. So it's just basically m binary numbers of like length n each. And then we must see if it is possible to have a set of like any set of conditions, like such that actually for each row, like each row has a value, You know, it's possible to see if it like if we can have any set of conditions that give the values for each row. Basically that's the general problem. Each condition is like an if statement checking one possible location for a certain value. Now, let's go into basically the full solution for this problem is actually pretty hard. It's pretty difficult. So let's first consider like some certain subtasks, because basically 2 to 3 have n equals 2, 4 to 5, and 5 have m equals 2. Now, because problem 1 and 2 of this contest are way easier than problem 3, the optimal solution for this contest should be like doing 1 and 2, and then possibly getting these 2 subtasks. And then this will actually most likely get you a passing score on like the overall contest, because these subtasks are way easier than solving the whole problem. So let's just first go into solving these 2 subtasks instead of solving the entire problem. So let's first address the n equals 2 subtask. So this means that there's only 2 columns. So every number is like either like 0, 1, 1, 0, 1, 1, 0, 0. We say that basically there's only 4 possible options for numbers in these in the n equals 2 subtasks. These are the only 4 possible rows. And this means that all we have to do is check whether all four of these numbers can be separated in distinct groups. Basically, it's if all of the 1 zeros have the same value, and all the 0 1s have the same value, and all the 1 1s have the same value, and all the 0 0s have the same value, like within their individual groups, then the whole thing is possible. And it's pretty easy to prove that. We can just write a set of conditions to satisfy this. So And again, we can see that basically if like two numbers are the exact same and they have different conditions, then they're obviously impossible. So like this is the values, if these are the values, then if it looks like this, like what two 1-0s have different values, then it's always impossible because they're passing through the same conditions. They'll like satisfy all the same conditions, and it would just be impossible for them to have different values. So for the n equals 2 test case, all you have to check is if we just have to separate them into these 4 groups of 4 distinct values. And if everything in like each group is the same as everything else in that group, then it's going to be possible. And if there's ever something different, then it's not possible. So this subtask is not too hard, and we can just solve it like this. And now moving on to the m equals 2 subtask. M equals 2 subtask means there's only 2 rows possible. There's only 2 numbers. So the numbers can be really long. It can be up to 100. It would just be like 101. I don't know. It can be like any number. Let's say that. However, we can see that if the 2 numbers are distinct in any position, then we can just we can create a condition that just separates these 2 numbers based on that one condition. So like let's say the numbers are like 1001, 1000, like 100. Well, first see like if they have the same value and they're like distinct in any one position, then obviously the problem is if they have different values, and they're distinct any position, then we can just differentiate them just by that one position. We just write one condition to separate them, and then it'll be able to separate them into these 2 values, and it'll be possible. So if the values are distinct, we just have to see that if the values are distinct, there just must be at least one position where the 2 numbers are distinct in order to fulfill the conditions and have it satisfied. And we can see that if the values are distinct and the numbers are exactly the same, then again, from the previous one, it's obviously impossible for this test case to be possible because you can't pass through 2 numbers with the same set of conditions and expect different values, right? So now onto the case where the values are different, are the same, so if it's like 1, 1, then all that needs to happen is that the 2 values must have one condition, must have one position where they are equal to each other. Like everything else can be like different, but there just must be like one value where these 2 things are the same, and then they'll be both past this one condition. And overall, actually no, if the 2 values if the 2 values are the same, then it's just always possible because there can just be an else statement at the end from this like example problem. There can just be like an else return 1 statement, and then this problem will be true. So if the 2 values are the same, we see that this problem is just immediately solved, and it would just be true. So now on to like the general problem. But again, like just by solving these 2 test cases and the first 2 problems, you will most likely already have passed like this contest. So when we see this kind of problem, like just first look at the sub cases, because first look at the subtasks, because oftentimes the subtasks are way easier than the general problem. And if you already have the points from 1 and 2, you can just go for the subtask first and try to instead of spending all your time going for the full problem. So now onto the full problem, full solution. Okay. The initial observation we can make is that as we add conditions, we are getting rid of we get rid of rows. We get rid of rows of inputted rows, right? Because as we pass this each number, each row through this condition, if the row passes that condition, that means that it's excluded from the rest of the conditions. So then that means that the row can just be basically removed, and we don't need to consider it as we continue on with this problem. And then so we can see that it is always optimal to remove inputs. Always optimal to remove inputs, as this just simplifies the problem, and just makes it easier. Because if we can reduce the number of inputs, then overall, like the problem just becomes a step easier and just no downsides to this. So that's the like observation we must make. So this is the observation. Now how this observation happens is it just comes with practice. We just see that basically, yeah, like rows inputs could disappear as we add conditions, and there's no reason we don't want like there's no reason we'd want to keep more inputs, as like lower inputs just makes the problem easier and reduces it to like an easier state. So then that means that we want any correct from this like observation, we can see that we want any correct condition is good, because it could remove any correct condition is good for our problem, because this will remove some inputs. If we can make this condition and pass them through, it will remove the rows that satisfy this condition. So now the question becomes how do we find all the optimal, like finding like correct conditions so we can like make, and we want to find all of them. And if we aren't able to find any correct condition, we can also then conclude that it is like it's going to be a lie for that test case, because there's no more conditions to make, so there's no more ways to separate out any of the two like values. So we want to just find all the correct conditions, and that becomes our next problem. So we can see that if all the ones and zeros correspond, like in a position, correspond to a single value, we can add a condition about that position and value. So like, let me just quickly bring an example. Like, let's say we have 1 0 1 0 0, and then this value is 1, and then like 1 0 1 1 0, and this value corresponds to 1, and 1 0 1 0 1, this value corresponds to 1, and then like 1 0 0 1 0, and this corresponds to 0. Okay, let's say we have something like this. Then an immediate observation we can make is that like the ones in the ones in the 3 position, in position 3, if it is 1, then it becomes 1. If it's not 1, it becomes 0. If it's 0, then it's not 1. So that means that the condition we can make here is that value in 3, if value in 3 in position 3 equals 1, then the like value is 1. Actually, I'm trying to like digit like number in position 3 is 1, then the value is 1. So that's a condition we can immediately make. And then like this is a correct condition, obviously, because like it satisfies it. And from our like initial observation, where like anytime we can add a correct condition, it's good. We can just quickly first just add this condition without any downsides. So then the question becomes, so like that's the way we do it. The way we create new conditions is if in a position, all values, like all ones or zeros correspond to a single number, a single value, then we can add that condition. That condition. Like again, like if it doesn't happen, then we obviously can't add the condition. For example, going back to this example case, if we just look at like the first position, it's all ones, but the ones correspond to different values, right? Like these 3 correspond to ones, and the last one corresponds to a 0. I mean, we can't add a condition there because there's no condition that allows it to be 2 separate values. And that's actually all we need to do. This is like the only condition. This is the only requirement that we need to satisfy a condition, because like we can make a condition around this. And from our observation we've already made, we say that any condition is good. So we just want to like, this is like the minimum possible requirement for a condition. And that's all we need, because we just want to add any condition we possibly can. So then now the question becomes like, how can we quickly implement solving this? Like, how can we quickly implement like finding these correct conditions? So let me just erase this observation part and do in the middle. Actually, let me just erase the top two parts. Okay, in order to find like this condition, if like all ones and zeros correspond to a single value, we can have an array keeping track of each position. So position from 1 to n. And then the value, so either 0 or 1. And then, oh, not the value, the number in that position, and then the value is either 0 or 1. So this is number in that position. And this is the value of like the row it's in. So we have this counter that counts for each, like the total, like for across all these rows, in each position, the number of like, for each number, the value it has, and we like add this for each row if it's true. So this, like this number counts across all rows and positions. So we can see that if in a certain position, right, let's say that in this example, from this example, position 3, if either all the ones, if either this is like the number of numbers where like has number 1 and value 0, and then this will be the number of numbers with number in position 3 with number 1 and value 1. We can see that if one of these is 0, that means that all the numbers are in like the other position. So then that means it will satisfy this condition that we're looking for. So for example, in this example, right, CNT 310, position 3, number of ones was 0. This is 0. And CNT 311 is 3 in this like in this case, because like if we count from these rows, the number of like numbers with number of rows with value 1 with number 1 value 0 is 0, and number of rows with number 1 in position 3 with value 1 is 3. You can see that this case, we're looking for this because this means that if this is 0, that means that everything else is in this case, which satisfies this condition here that we're looking for. So basically the equation then becomes if C and T, like any position I, J, either 0 or 1, if one of these equals 0, then that means that everything is in the other case, like all the values in that position and like in that position and number correspond to a single value because the other one's at 0. Then that means that we can add this condition of IJ corresponding of like position IJ. This will be our condition, like if statement condition corresponding to the certain value. Now, in order to like optimize the solution, we can create a, let me just erase this part now. So we count if this is true. And then that means that we just have like a list of conditions IJ that we have. But however, many of these conditions could be added at once. Like as we first loop over the array, we're adding many of these conditions. So in order to actually code this, we use a queue to store all of these conditions IJ that we've added. So as we encounter like one of this happening, we just enter in IJ into a queue, and then we process these conditions one by one. Now, in order to process the conditions, all we need to do is like find rows that satisfy the condition and remove them basically, and then remove. Because going back to our first observation, all we're trying to do is removing rows as we add conditions. And in the end, we're trying to get 0 rows remaining, as that means that all of these rows have been filtered through the conditions. And that's the outcome we're looking for in order for it to be true. And if we can't do that, that means that the total thing was false as we can no longer remove any rows. So as we remove rows, then we have to update this CNT function that we have. We have to update this value. We set this all at the start, and as we remove a row, we can just remove all the counts in this like count array by looping through the one we removed and subtracting the values of C and T that correspond to it. And then as we do this, we are looking for new values of C and T that work, like satisfying this condition. And as we find them, that means that we've created a new condition and we re-enter it into the queue. So we just continue doing this until the queue is empty and there's no more conditions, or until there's no more rows remaining. So, and if there's no more rows remaining, then that means that we've solved this problem. And if there are rows remaining and no more conditions, that means that we also solved it, and the answer is alive for that one test case. Does this make sense to everyone? Overall, this problem is really complicated for a Bronze 3. But again, if you solve questions 1 and 2 and just get this half-point subtasks, both n equals 1 and m equals 2, both n equals 2 and m equals 2 subtasks, you are going to be able to pass this contest, because you'll have around 800 points, which is basically enough to pass any contest. So does anyone have any questions about this solution?
Can I ask what's the J?
J is the number in that position. So I equals position, and then J equals number in that position. The value this corresponds to, for each condition, doesn't matter too much, because all we need to do, it doesn't matter what it actually corresponds to. All it matters is that we're able to write a condition with this position and number, and then filter out all the inputs that have this number in that position. And then once we filter out the inputs, then we can see that the problem gets reduced down, and which is what we're aiming for. Does anyone have any other questions? Okay. So with that, let's go on to teacher Ren. Can you screen share the slides again, maybe?
Yes. Let me share my
teacher
screen and
okay.
switch slides. Yes.
All right, great. Now, after we finish problem explanation, I'll explain how this contest ties into our XCamp classes, and how we teach at XCamp. They teach the required knowledge necessary to solve this contest. So overall, there's many XCamp classes throughout the year. There's year round, there's going to be weekly classes ranging from beginner to USACO Platinum and camp levels of systematic knowledge build up, and this lasts for 4 quarters a year. It's just weekly all year round. There's occasional breaks for holidays, but in general, it's just every week. This teaches just fundamentals new algorithms and problem solving skills all throughout the year. And then next, there's a winter camp and a summer camp with it's going some winter and summer camps are on site, and they provide way more training and practice. The camp lasts for around basically the entire day, over winter and summer camps while it's active. It's the entire day. You spend the entire day just solving problems with other people from this camp. And then it's one of the best ways to improve a student's abilities, as you're basically spending an entire day for weeks coding and practicing problems. You get to meet a lot of new friends, and overall it's just a pretty good time, and you also get to improve a lot over this intense period of training. Next, there's enrichment classes, which consist mostly of mock tests. So mock tests are basically essential in order to solve the more and more complex problems, especially the ones requiring observation and intuitions. These mock tests train problem-solving habits, and also just allow you to handle stress and frustrations, as well as teach you strategies about during a contest. Most of these problems we went over today, the 3 problems, especially number 3, just required a lot of intuition. Like you had to make those observations that, for example, for problem number 3, you have to make the observation that you just want to add as many conditions as possible. That's like not a super simple observation to make, especially if you haven't done as many contests. So the only way you can actually train yourself to make these observations is by taking more tests, seeing more problems, because this isn't really an algorithm you can memorize. You just have to like be able to see these patterns as you do more problems. So this mock test, like it's just a lot of tests. It's just like 1 or 2 tests every week with teachers to go over these problems and teach like contest strategies as well. So overall, it's a great way if you want to quickly improve at taking contests such as USACO. It will teach you like important strategies. Next, we have a masterclass for USACO Gold, Platinum, Camp, and US team members. This is like for really advanced participants who want to aim even higher. So for people in USACO Gold, it's for them to like reach Plat, and for people in USACO Plat, it's for them to like reach USCamp and like possibly represent the US at IOI. So at this class, there are teachers at XCamp with world-class abilities. These teachers have won like gold medals at IOI. They're some of the best coders in the world. And yeah, you can't actually get this coaching anywhere else. Like I haven't seen any other coding institutions with teachers of this level of like ability. I haven't seen any like IOI gold medals at like anywhere else. So yeah, basically in order to like reach even higher, you want these teachers because they've gone through these same experiences themselves, and they have like important like knowledge they've learned from all their years of coding, and they're able to like teach like even the hardest problems, as like they're the ones who are able to solve like the hardest problems in the world. Now, in order to prepare for the next USACO, one of the best things is, again, the mock test class, as they are able to simulate a competition experience, and through like repeated simulation of competitions, you're able to obtain more contest strategies, learn about these like observation and intuition, learn more about the observation problems, and overall just improve your coding ability. It also like teaches a lot of contest strategies, which is actually extremely important for these contests. Like if you're like just looking to pass past USACO levels. For example, in this contest, one strategy we probably could have employed was just going for problems 1 and 2 and then subtasks on 3. This would have enabled you to pass bronze this contest, as like solving the entirety of problem 3 is way harder than solving the first 2 subtasks. So if you just solve the first 2 subtasks, you still would have probably like passed bronze, and this would have just yeah, without even like doing like the hardest problem of the contest. So like this mock test classes teach you strategies such as this, as well as just overall problem solving strategies. And if you're looking to perform well next USACO, I highly recommend this, as it is like the most tailored for just taking USACO. As well as this, there's an XCamp winter camp for boosting your contest performance. Currently, only gold and platinum camps have openings left, but there's possibly openings that may open up. So if you're looking for just like 2 weeks of like extremely intense like training, it's like you'll see like great improvements in your coding ability over this time. And yeah, I recommend signing up for the XCamp winter classes camp as well. As well as this, there's also just the XCamp weekly class for just building up your knowledge, like coding knowledge and just doing problems as well. These classes just meet once per week and are open to all levels, and they teach various algorithms and problem solving skills that are important for just passing all levels of USACO. As you get better at coding, you can move up the classes at any time. And this, like XCamp is extremely flexible about this. Like you just have to like talk to your teachers. If you think you're ready for the next level, they'll judge you if you're ready or not, and then they can just immediately move you up. So it would just like these weekly classes allow you to like move at whatever speed you want. You have to learn all the algorithms needed to pass certain levels. And then after you have the knowledge required, you can just move up again. And as well as this, we also just have monthly USACO public USACO mock tests for bronze, silver, and gold divisions. And by submitting to this link here you see on the slide, you'll be able to see instructions in order to get these like highly curated problems that closely resemble actual USACO problems and can help you study for the next USACO tests. So now we have a Q&A session as well as some information listed on the slide if you want to get in contact with XCamp.
Thank you, Alex, too, for all the explanations. I think we are run of time. The zero level have been joined. Thank you all for all the students, for the bronze students who attended these sessions. Yes, if you have any questions and want to learn more about XCamp, here are the links here. Okay, Alex, thank you again. Yeah, for the bronze students, you may leave now, but if you are interested in zero problems, you can still stay. The zero is much, much harder than the silver problem. Yeah, thank you, Alex, too. Bye, bronze students. Stay here, silver students.